Good morning, ladies and gentlemen. All right, we have people awake. My name is Christian Kirchev, and I am the core compiler lead at Ada Core. Today, I'd like to introduce you to Spark 2014, which is the new addition to the Ada Core family. Now, before I start, two notes. One, I'll refer to Spark 2014 as Spark because it's easier on my mouth. And two, if you have any questions, feel free to interrupt. So, this will be a fairly comprehensive presentation because it assumes you have no prior knowledge of Spark. So, I intend to go over the following major topics. I'll first start by explaining what Spark actually is. Then I will go into the various applications and the amount of effort it would take for you to adopt Spark in your software. Then I will share with you our short-term and long-term plans for Spark. And finally, I'll finish by giving you some useful information as to how to get started with Spark. So, what is this Spark thing? Well, Spark is a new programming language developed jointly by Altron UK and Ada Core. Spark is based on Ada 2012, and it excludes features which are either too difficult or impossible to analyze automatically. Spark adds its own layer of semantics on top of Ada by introducing brand new constructs, as you will see, and at the same time, it restricts existing Ada features, making them more suitable for safety-critical applications. The main goal of Spark is to provide software verification using formal methods. For those unfamiliar, formal methods are mathematically based techniques such as automata theory or logic calculus for the specification, development, and verification of software. For those parts of your application where you've chosen to use a different language, or you have intentionally decided to violate Spark semantics, you would still have to revert to good old testing to show verification and coverage. Spark is a high-level programming language by design, but it shines really well in safety-critical contexts such as DO178C and DO333. DO178C is the avionics standard, and DO333 is the introduction of formal methods to avionics software certification. So this is where Spark is positioned. Essentially, prove as much as possible using formal methods and minimize the amount of testing or altogether eliminate it if possible. The language is powered by some very powerful tools. The Ganad Pro compiler is in charge of Spark semantics and code generation. Ganad Proof, which is really the heart of Spark, is both a full flow analyzer and the formal verifier mixed into one. For those parts of your application where you cannot apply formal methods, Ganad Test, as Quentin explained, comes to the rescue because it generates test harnesses for you and leaves it for you to fill in the blanks and do the testing. All these three tools have already been fully integrated into our two flagship IDEs, GPS and Ganad Bench. Now let's see how Spark compares to Ada in terms of semantics. What I have here is a little snippet of code from a package which performs ballistics calculations. The idea is, given a topographical map coming from this package, an origin and direction of projectile, and some initial speed, function impact point calculates the impact point. As you've probably noticed, both specifications are identical. Well, on the right, it's almost Spark. So this is what real Spark looks like. Don't be scared, it's not that bad. All these new items which appear on screen are called aspects, and you will learn everything about them during this afternoon's presentation at 2012. But Suffice to say that in the context of Spark, aspects are used to express contracts. And you've been hearing about a lot contracts, you will hear a little more. Contracts are really the cornerstone of Spark because they have the ability to express both functional and data relational properties. Contracts can be applied to packages, subprograms, any kind of body, objects, types, and generic instantiations. So let me give you a little taste for the semantics. Spark mode on means that package ballistics and anything declared inside it will be subject to Spark semantics and can be formally proven by the tools. This is, by the way, how you turn Ada code into Spark code. It's just by adding this annotation and boom, you get magic. Abstract state indicates that package ballistics will contain some internal library level data which is available to the outside as an indirection called an abstract state, and its name is trajectories. Going further to the function, pre stands for precondition, and it specifies the input requirements of the routine. In this case, we want the origin of the shot to be on the surface of the map. We don't want to be shooting at our feet, and the speed must be such that it propels the projectile. Post stands for postcondition, and it expresses the output requirements of the routine. In this case, the resulting point has to also be on the surface of the map. Now, these two annotations, pre and post, and in addition to another one which is called contract cases, specify the functional properties of the subprogram. This is also a great way to express low-level requirements in the context of DO178, and it's also a great way to decouple defensive code from any implementation whatsoever. The last two annotations deal with the data relational properties of the subprogram. Global is used to specify, or we should say to classify, any additional input or output that this subprogram is supposed to read or write. In this case, we're saying that we'll be using this internal data trajectories and we'll be extracting some data from it. And finally, depends expresses how the inputs and outputs relate to each other. In this case, the impact point will be generated using the data from the origin to the direction of the speed and the trajectories. Well, you're probably thinking, well, that's silly. Of course you're going to be using the formal parameters in this thing. Well, here's a hypothetical. Say in your algorithm, in your implementation, you forgot to read this, or you actually read it, but you discarded the value, and it doesn't really participate in any meaningful way in calculating the result. So, is this a design problem, or is this an implementation problem? Well, up to you really, but the point is, it is thanks to these kinds of annotations that Spark and Gannett-proof can find these kinds of problems. Now that you know what Spark looks like and what it is, let's see what the language and the tools can do for you. Right off the bat, you can use Spark as a safe coding standard for critical and embedded software because it already excludes features which are deemed too unsafe in that kind of context. For instance, you don't want any kind of heap management or exception propagation in safety critical software. Gannett-proof also comes to the rescue in this mode of operation by using its flow analysis mode. It will help you detect errors related to things such as uses of uninitialized variables or parameter aliasing, or for instance, code which has been rendered obsolete due to value propagation, for instance. The second point, which I think is a big achievement, is formally proving the absence of runtime errors. Well, this is huge, so let's put this in perspective. Ada and Spark are safe and robust languages because pretty much every operation is scrutinized either statically or by means of a runtime check. What Gannett proof can formally verify is that no runtime check can raise constraint error, that no assertion can fail and raise assertion error, and that no user exception could possibly be raised. If this is not the case, then Gannett proof will point you to the exact culprit, will also give you the path in the code and the values which led to this problem manifesting. Now this is a very important type of proof, because once you achieve absence of runtime errors, you can throw away any kind of exhaustive or robustness testing. So think about it. What impact does this have? Achieving ARTE really requires a few contracts. From the previous example, pre-post and contract cases. So you actually need very little to achieve this kind of property. Oh, and full flow analysis, by the way. The success rate of ARTE is in the 95 to 98 percentile, assuming all of your code is in Spark. In order to cover the last percentages, you still have to fall back to good old testing, but it's just what, 5 to 2%? Not bad. A very nice property is the optimization of runtime checks. So once you prove absence of runtime errors, you can request the compiler to build an executable without any form of runtime checks, effectively reducing the footprint of the executable and improving its performance, because you're not going to be executing useless code, essentially. Proving absence of runtime errors is kind of a localized property. But we can do better by going up the development ladder. So now we can prove something called functional correctness. So recall function impact point from my example. Let's say now that you have the specification and the implementation written in Spark. Both of these carry their own sets of contracts. And what functional correctness will do is it will prove that what you've implemented is really what you have been advertising in the spec. Once you prove functional correctness, you can throw away any form of unit testing. We can do even better than that. Now we're looking at the programs. Let's go up and look at component integration. Notice that components may have been successfully verified on individual basis, but may still malfunction when you bring them together because, let's say, you have poor design. What Gannett proof can do in this case is it can show that components essentially play nicely with each other and they respect each other's contracts. Because component integration already assumes functional correctness and full flow analysis, you only need to utilize pre-post conditions and contract cases in proving this property. So this is just a handful of the various applications of Spark in various contexts. For the full list, you can check the Spark user guide, and I'll give you a link towards the end. But you should notice the predominant theme. Prove as much as possible using formal methods, minimize or altogether eliminate any form of testing. So at this point, you're probably thinking, this Spark business is pretty nifty technology, but what amount of effort would it be for us to adopt it to our existing software, for instance, without having to start from scratch? Well, the good news is that Spark was designed with gradual adoption in mind. The language has the ability to permeate existing Ada code by selectively including subprograms and units and components in its closure by utilizing the Spark mode on annotation. This in turn allows you to apply the layer of Spark semantics on top of Ada at your own pace and at the same time introduce contracts. The more elaborate and expressive your contracts are, the higher the level of verification you'll get in the end. One really important point to make here is that thanks to this gradual adoption, you can keep your existing team of engineers. It is much easier for Ada experts to become Spark experts rather than having to bring in a whole new team into an already streamlined software development process. Because Spark is a first-class citizen in the Ada core ecosystem, most of our tools work with Spark code out of the box. For instance, you can still continue to use project files to express complex build dependencies, or for instance, you can run Ganat stack to get stack probing. It is not just a language that's flexible, but so is the Ganat proof tool. For instance, you can run Ganat proof on a single line of code to prove, say, absence of runtime errors. Or you can go to the level of a subprogram, or a unit, or your whole application. On top of that, you can customize the tool to run in different modes. You can run it as a flow analyzer and prove things such as, for instance, lack of aliasing of parameters. Or you can run it in a formal verifier mode, prove functional correctness, or you can do both at the same time. Because Ganat proof is already integrated into GPS and Ganat bench, in addition, you get advanced result queries. For instance, in the IDEs, you'll be able to see the path leading to a problematic area, and with addition of a feature called counterexamples, you will get the values which brought you to that abnormal situation. This in turn greatly facilitates your debugging effort and your recovery effort. So Spark was first released 2 years ago, but the language is still undergoing evolution. This next year's release will contain support for the Ravenscar profile of tasking. What this means is that Ganat proof will be able to formally prove that you have no data races and that you have no deadlocks in your application. In addition, we're rolling out a feature called Ghost Code. Ghost Code is really a zero footprint, non-intrusive way to instrument your code. So let's make a little observation here. Once you prove correctness, any type of contract or any auxiliary routine that you may have used in that proof becomes obsolete because you've proven correctness. What Ghost Code allows you to do is you can write your contracts and additional skeletons and infrastructure aimed at proofs in a way that, first of all, does not affect the behavior of your software, and can be easily, literally yanked out of the final executable. So in a certain sense, you exercise your code, and all ghost stuff disappears from your final executable. Finally, we're adding support for subtype predicates, which is a fine-grained way of specifying constraints on data sets. It's not just the language that's undergoing improvements. We are beefing up the internals of the Ganat proof tool by providing support for 2 additional theorem provers called CVC4 and Z3. We're doing this to provide better diagnostics and more accurate proofs. Finally, I already mentioned counterexamples, but you could think of this as a static debug dump. Anytime Ganat proof detects a problem, you will get really the values which brought you to that point. Maybe in a future release, counterexamples would be able to generate actual physical tests that you can immediately run and verify for yourself that this is indeed a problematic area. Some of the long-term plans for Spark is to add support for access types, pointers, and some kind of heap management. This is very hard to do because once you introduce data aliasing, static analysis just flies out the window. So our language designers are hard at work to try and figure out how to make this relevant in safety critical contexts. In addition, we're planning to integrate CodePeer into GNAT-Proof because, as it turns out, CodePeer is very good with floating point related queries. Currently, GNAT-Proof is, well, it could do better with respect to floating point verification. Let's put it that way. Finally, in parallel to all of this, we would like to provide Spark-like annotations for C code, achieving a whole new level of integration of these two languages. And finally, we're looking at providing some form of metrics or indicators for formal development. This is most likely going to be a visual representation of proof coverage, let's say. But this is still under heavy development. So now that you're all excited about Spark, let's see how you can get started with Spark. There are two major sources of information. The first one is the GNAT reference manual, which is structured after the Ada reference manual, and it discusses the syntax, the semantics, and the verification rules of the language. The other one is the Spark user guide, and it lists all the relevant uses of Spark in various contexts, and it also covers working with GNAT-Proof. Both of these come with plenty of examples to get you started. In parallel to all of this, John McCormick and Peter Chapin are authoring a textbook on Spark, and in addition, AdaCore is offering tutorials, webinars, and training through our AdaCore University website. Here are some additional resources for you to follow. We make major announcements regarding SPRO at the official Spark Pro website. The Spark community webpage is basically the largest knowledge base on anything Spark. Here's the link to the user guide, and if you replace UG by RM, you'll get the reference manual. And finally, drop by through the AdaCore University once in a while for the occasional jam or course. So, what I'd like you to take away from this presentation is that if you want to get guarantees about your software at a reasonable cost, with the same team, tools, and processes, then choose Spark. And remember, AdaCore is here to help. Thank you.